Yeah, I will talk in the framework of variational data assimilation. It means in a deterministic frameworks. So basically, in the most simple way to define sensitivity is the evaluation of a gradient of some response function with respect to parameter. If you want to predict, you will need both a model and observation. And the question is how to evaluate the impact of an error on the observation in the prediction, for instance, on the retrieval of the fields. The question is observation and models are linked only in the optimality system. There is no other link between models and data. Therefore, the heart of the problem is, in this case, sensitivity analysis has to be carried out on the optimality system rather than on the model. So we consider some model in the abstract form, f of x and u equal to 0, and we assume that the model has a unique solution x depending on u for each u. We introduce some scalar response function, which is g of x and u, and by definition, the sensitivity is the gradient of g with respect to u. So this is the definition of the sensitivity. So how to compute the sensitivity? To do it is very simple to show. We introduce an adjoint variable, capital P, as a solution of df over dx transpose. df over dx is the Jacobian of the model. P is the adjoint variable is equal to the gradient of the response function with respect to the state variable. Then it's very simple to see that the sensitivity is equal to the gradient of g with respect to the parameter minus the transpose of the Jacobian of the model with respect to the parameter multiplied by the adjoint variable. So this is the abstract form. Now we go to the problem of variational data assimilation. So phi is the state variable, solution of d phi over dt is equal to f of u, and the control parameter is the initial condition phi at time 0 is equal to u. So as usual, we introduce a cost function depending on the initial condition u, which is, roughly speaking, the discrepancy between the guess of the initial condition and the error in the observation. V1 and V2 are supposed to be the equivalent of the inverse of the operator. So U0 is the first guess, and C is the linear bounded operator from the state of the initial condition, capital X, and V2 is an operator in the space of observation, and they are supposed to be symmetric definite positive. Of course, it is something looking like the covariances. Okay, so this is the problem of variational data assimilation, and the game is to minimize J. To do it, as usual, we introduce the adjoint problem and the adjoint variable. Phi star is the adjoint variable. the first equation is the model itself. The second equation is the adjoint model. So with the final condition phi star at time capital T is equal to 0, then from it's not very difficult to see that the gradient of the cost function with respect to the initial condition is equal to V1 multiplied, this is the last equation, U minus U0 minus phi star. And the necessary condition for optimality is that the gradient should be equal to 0 at the optimum. So this is the classical variational data assimilation problem. So now we want to know how to evaluate the sensitivity with respect to the observation. If there were some error in the observation, what is the propagation of this error? So we have to perform this computation. dg over d phi ops is equal to this derivative. Okay, and we are going to proceed as we did in before. So we put a perturbation on the initial condition. Oh, excuse me, oh, it's not very clear, sorry, no pointer. So basically, we put a perturbation delta phi ops. The perturbation is on the observation. Then there is a perturbation on the model itself. And the new initial condition is delta U. There is also a perturbation on the adjoint model, and we need the Gatto derivative of the adjoint model, which is the second equation. So we have this system, and from this system, it's possible to compute dg over d5. So how to proceed? We have to introduce, to compute the gradient, we need to introduce three adjoint variables. Three adjoint variables add the second order. And what we do, we take the inner product of the first equation of the perturbed system with P1, of the second system with P2, and what we find that P1 has to be solution of the first model minus dP1 over dt minus the derivative of the model transpose P1, and P2 is also introduced in this model, and we have also the second adjoint variable in the second equation, and the third adjoint variable is in the initial condition of P2. So we have to excuse me. Okay, sorry. So this is the system we get with P1 and P2. And what is interesting to notice is there is a final condition on P1 at the final time. P1 at time capital T is equal to 0. And we have a condition, an initial condition on the equation with P2. Therefore, we have a coupled system with one equation, they are coupled with P1 and P2, and one equation has an initial condition, and the other has a final condition. With some manipulation, it's easy to see that in this case, the sensitivity, dj, j being the test function, is equal to V2 CP2. It means that we need to solve this system to get the sensitivity of the response function. So this is equivalent to an equation in the space X of the initial condition, capital X of the initial condition, which is HV is equal to F, and the right-hand side is the derivative of the response function with respect to U, plus phi tilde star, which phi v star, which is a solution of something looking like the adjoint model with a forcing term, which is equal to the derivative of the response function with respect to the state variable, with the final condition at time capital T. So, to compute the gradient of G, first we need to solve the equation 30, and with the variable phi tilde star, with the final condition phi tilde star at time capital T is equal to 0. Then we need to solve the problem with the operator H. HV is equal to capital F, with F, which is equal to the partial G over du plus the solution phi tilde star at time t0. Then we solve another problem with P2, the second adjoint variable, with an initial condition, and once this system has been solved, then we can compute the gradient of the response function at G over the derivative with respect to the observation, which is equal to V2 CP2. So this is the basic algorithm to compute the sensitivity. We did an application with a 3D thermodynamics problem applied to the ocean, to the Baltic Sea, and capital T is the temperature, T is the derivative with respect to time, and this is a 3D model. And the only unknown here is the temperature, capital T, all in the first equation. The initial condition is known. Then we have a condition of flux on the surface of the ocean, which is dt over dz is equal to q, and q will be the control variable. It means that we want to optimize with respect to q. Then we have coherent boundary condition, so the problem is to find the flux on the surface. So the model can be written on this operator form. There is no, is a weak sense of the equation. And the problem of data assimilation is to determine Q, minimizing this cost function, and the observation, the solution is with the temperature on the sea surface. Okay, and we have a first guess of the flux, which is Q0. So this is the basic problem. And what we want to do is to evaluate the sensitivity of this solution of this problem with respect to the observation. So in this case, this is the optimality system. We have the model itself written on a more simple form, and the equation 30x, excuse me, is the adjoint model, and 39 is the optimality condition for Q. So this is the optimality system. So what we want to do, if we want to evaluate the sensitivity with respect to T-ops, which is the observation, we will have to derive this optimality system. Okay, so as we did before, we introduced two adjoint variables, P1 and P2. And what is interesting to see is that we found a non-standard problem. The variable P1 at a condition P1 at the final time is equal to 0, and P2 as the condition at time t0, it means at the initial time. And what we see is the gradient of the response function is equal to m0 P2 at the elevation z equal to 0. Okay, so to write, we can write the model under an equivalent formulation, and this is the equivalent formulation for the model. I will not go into the details, and symbolically, it can be written HV is equal to 5. With the details. This is the operator 5, and will not give everything. So basically, we have a second order adjoint model. And what is interesting is that HW is equal to alpha W plus phi star. Phi star being the solution of the second equation. What in this case, because we have to deal with a linear model, is H is positive definite, then we have a unique solution, and the equation is everywhere solvable. So the non-standard problem, which is a problem we have seen before, is unique, as a unique solution. So to summarize, this is the algorithm to compute the sensitivity. First, we solve this adjoint model minus d phi tilde star is equal to this condition with a final condition at time t1. And we put capital phi is equal to value of phi at the initial time. Then we need to solve HV is equal to phi with this capital Phi given by the first equation. Then we need to solve the equation with the second adjoint variable with an initial condition. Then from P2, we determine the sensitivity which depends on P2 on the sea surface. So some numerical tests were done on the Baltic Sea. So this is the topography of the surface of the Baltic Sea. We have 3 or 4 squares, which are the location of the observation. There is 2, 3, 4, and there is 1. 1 is there. 1, 2, 3, 4. This is the place where the observation. Then we deduce here the, it was already on the first slide, the gradient of the sensitivity with respect to the observation. Okay, it's not very easy to write and to present, but anyway, there are applications we work, or some other people are working on, which is, for instance, the optimal location of sensors, and there is a lot of information in the matrix associated to, in some sense, to the covariance of the sensitivity, and more will be done later. And to conclude, I just show you, would like to thank these guys, and if you don't, it's Balakrishan, Marchuk, and Lyons. I guess it was in Novosibirsk in the 60s. I don't know what they are drinking, but okay. Okay, so bon appétit.
Questions or comments?
So I don't know if you might have actually said this, but basically you do assume that you have only one solution of your optimality problem, right?
Yeah.
Because otherwise, if you have more than one solution, you have more than one sensitivity, you know? Yeah, if you know.
We are always in the case where there is a unique solution.
Is there any way you can guarantee this in the application you have, or?
No, because it's in general, in data assimilation, in variational data assimilation, you assume that the cost function is locally convex and you are in the vicinity of a solution. It's a very local analysis. It's not a global analysis on all the domain, because you have nonlinear problems. No, in the observation. To predict, for instance, the evolution of the ocean, you need model and observation. And if there are errors in the observation, what is the impact on some response function?
You said that in order to determine the sensitivity of some output with respect to observation, it is not sufficient to do directly on the model, and so that the proper way is to do what you've presented, which I totally agree with. But is there any evidence, either numerical or otherwise, to which degree the two approaches, the naive one, I would say, and the one you've presented, differ in the end? For instance, in the
there is only one approach in this sense.
the correct one, but there is the naive approach, which is
naive approach. But, the naive
which
approach
you said is not the correct one, but this is what
the naive approach is to compute finite difference.
yes. But then, is the final result significantly different? Is there evidence as to the degree of difference between the naive approach?
If the dimension of the space of observation, you have to perturb all the observation, and if there are millions of observations, the naive approach is not very easy.
Okay.
This is why the adjoint method has been introduced, because we can also, for variational method, compute the gradient by finite difference. But
yes, of course, you have a sensitivity to all observations at the same time, of course.
Yeah.
Any other questions or comments? If not, it's time for lunch, and let's thank all the speakers of the morning session. Thank you very much.